So we've already seen how to multiply a normal number with a normal number and get a normal result. And we've seen a possible method of allowing us to extend this to subnormal numbers. So let's go ahead and we'll look and see if we can implement that now. If you go to the resources section, you'll see a file there. If you go and open that up and make sure you're on the Tools tab, and you'll have several options here. So we're going to choose floating point multiplier, so just click on that and it'll run up the multiplier. Now we're going to multiply together 1e to the minus 40. Now this is a subnormal number, and you see it says subnormal here, and we'll multiply that by 1000. Now 1000 is a normal number. Now it hasn't actually gone through the multiplication because I've stopped the program in order to see it before the normalization. But we're going to have a subnormal number times a normal number, and the answer is going to be a normal number. Now there's a reason why we want to go through this one first, because this is going to give us the same sort of result that we got whenever we just did the normal with the normal and get a normal result. So let's have a look at this now. You can see that the subnormal number is the x number, and that's the x number here. Now what we're going to do is we're going to take this subnormal number, and you can see that you can obviously see the number down here as well, and we can count the number of leading zeros in the significand. So the number of leading zeros is going to be 1, 2, 3, 4, 5, 6. But remember, there's going to be a 24th bit as well, which is an understood bit or a hidden bit. And for a subnormal number, that will have a value of 0. So whenever we actually count all of the zeros, leading zeros, we're going to actually have 1, 2, 3, 4, 5, 6, 7. So this leading zero count, and what I'll do is I'll call this a pre-leading zero. So this pre-leading zero count is a value of 7. So let's now go and we'll see how we can, if we press OK in this, it'll actually run through the multiplication and it's generated the correct answer. We've got our exponent here and our mantissa here. So we'll go now and we'll see how we generated that exponent and generated that mantissa. So I'll zoom in a bit in this so we can see it a bit better. Now our ye is the biased exponent for our y value, which was our 1000, and that's a value of 136. We take away the bias, which is 127, and we get our unbiased exponent, which is a value of 9. Now this is a bit where it's slightly different now. The exponent value for a subnormal number is all zeros, and in that case what we do is we would use the exponent of minus 126. Irrespective of what the subnormal number is, the exponent would always stay fixed at minus 126. But now we're going to change that, because what we're going to do now is we're going to take that minus 126 and we're going to subtract off that leading zero count. So the leading zero count, if you remember, was a value of 7. So we subtract that off and we get a value of minus 133. When we add these two together, we get minus 124, and then we add on the 127 in order to get our biased exponent. So the biased exponent here is going to be a value of 3. Now that's not us finished with the exponent, because you'll notice up here that the decimal point is at this point here, and we still have to normalise this. So in order to normalise that meaning that we have to start with a leading zero, we're going to have to move the decimal point from this point here up to this point here. But in moving the decimal point from this point up to this point, again we're going to have to increase the exponent. So there's going to be a little bias here in the exponent of a value of 1. So what we do is we take the 3 plus the 1 will give us a value of 4. And this value of 4 is the correct exponent. Now, in order to get the mantissa, again, we start off with the decimal point here, and we know that in order to normalise it, we have to shift the decimal point up one place. So the decimal point goes to here. So everything that is left of this new decimal point, that's the 23 bits left of that decimal, right of the decimal point, is going to be the mantissa. So the mantissa is going to start 0, 0, 0, 1, 0, 0, 0, 0, and so on. So that's us generated our exponent, and we've generated our mantissa. Now, if we were to, in fact, I'll show another example where we don't have a leading 1 here. The leading 1 is in this position. But you can see from what we've done so far that we have the same setup now that we did previously. The only difference is that the unbiased exponent, the subnormal unbiased exponent has changed, and it's changed by that leading 0 count, or the pre-leading 0 count. So in this case it's a value of -7, and this would give us our new value for our unbiased exponent. But we can just use that new value for unbiased exponent the same as we did previously from that point onwards, and it's just exactly the same as multiplying a normal by a normal and getting a normal result. So let's have a wee look at one other example. So here's our second example. I've used the same number 1e to the -40. Now I've used the number 10,000. I've also swapped these round about, so the subnormal number was down here, it's now up there, so it doesn't make any difference, it just changes them in here. So you can see here that we're going to have the subnormal number is the y, so the exponent is a 0, it's -126, and we have to take away the leading 0 count. Now in this instance the leading 0 count is the same, it's 7, so we take that away, and the normal number is now 10,000, and it gives a value of 13. We add these two up, we're going to get an answer of -120. We add back on the 127 to give us a biased exponent, and that biased exponent is 7. Now the difference in this one here is that the leading value here, or the value after the decimal point, is a 1. So it means that we don't need to shift the decimal point because we already have a leading 1. So it means that this bias value here is a value of 0. So we're simply left with a value of 7, and 7 is our exponent value. And also the mantissa, we don't have to shift the decimal point to the left, we just leave it where it is, and the mantissa are the 23 bits to the right of the decimal point, so it's going to start 0, 1, 0, 1, 0, 1, and you can see that up here, 0, 1, 0, 1, 0, 1, and you can see here as well that the exponent is the value 1, 1, 1. So that's us talked through everything we need to know about the normal times a subnormal giving a normal result. So let's go and we'll write this down and make sure we understand it. So just before we finish here, let's recap on what we've done in subnormal numbers. We started off looking at introducing subnormal numbers, and we've seen that we had 3 problems. The unbiased exponent, it's fixed at -126, and also whenever you multiply normal with a subnormal numbers, it sometimes would tell you in certain circumstances that you were actually getting a normal result when you weren't, you were getting a subnormal result. And thirdly, the 8 bits was not wide enough to get the full range of exponent values. So the solutions that we come up with is to normalise the subnormal input and extend the exponent range to 9 bits. And finally, the subnormal exponent would change from -126, which was a fixed value, to a variable value, and it would be given by -126 minus the leading 0 count. So we've worked through a couple of examples and you've seen that actually working. Now let's summarise what we've got finally here. What we need to do is we need to ensure that the subnormal exponent, so that could be the exponent for either EX or EY, whichever one was the subnormal number, is going to be given by minus 126 minus this pre-leading zero count. Now, if we ensure that that is the case, then that's going to take care of the problems we have with problem number 2. So we're not going to get this problem of normal numbers times a subnormal number telling you you had a normal result when you don't, as long as we ensure that this is the case. So it means that the new value for your EX or your EY would be this value here. So as long as we are putting this value here in for our EX or our EY, then we're okay. So it means that the exponent would then be given by EX plus EY plus 127 plus the 0 or the 1. And also the mantissa would be a left shift of either 0 or 1. Now these two here are exactly the same as the normal times the normal, giving a normal result. So it means that by shifting the changing the subnormal number into a normal number, we can use exactly the same setup we had with the normal times the normal, giving a normal result. The only one proviso is that the subnormal exponent has to change, and it changes as minus 126 minus the pre-leading zero count. So I do suggest that you go ahead and open up the tool and put a few numbers in yourself and try a few examples and follow through the same route that I did in the examples in this video. Now we've covered two options here so far, the normal times the subnormal giving a normal result, and the normal times the normal giving a normal result. Now we've got two other options to look at, and that's whenever we have a subnormal answer. So we're going to look at the normal times subnormal giving a subnormal, and the normal times normal giving a subnormal. But we'll get onto those in the next couple of videos. So thank you for listening. I'll get you on the next video. Goodbye.